All right. So I work on AI for decision making, and more recently, I've been spending a lot of time thinking about building foundation models for all areas of science. And I know that not everyone in the room is a working expert in AI, so I just want to take a few minutes in the beginning to walk us through what has happened in AI over the last 15 years. So there are these different AI paradigms that have become popular. The first one is called supervised learning. And what supervised learning is you take in high-dimensional data input, in this case it's an image of an urban scene, and in this particular case, an annotator, an expert, has annotated this scene in a semantic space where every pixel is labeled as, for example, sidewalk, road, car, pedestrian, etc. You collect a few 100,000, a few million, tens of millions, 100 million of these examples. You feed it into an AI model, and the AI model is trained to decode input images in the same semantic space as these labels were generated in. And this is very popular. This works extremely well. It started working really well around about 15 years ago. And this is exactly how your self-driving car works. There are millions of neural networks, I actually helped contribute to a few of them, that are in self-driving cars, in your Waymos, your Teslas, your Mobileye's, that are running this software right now. But there's one issue, and the issue is that the labeled data is extremely expensive to acquire. In particular, in this example, what you typically do is you hire a professional labeler who you pay about $50 to $100 an hour to carefully label it pixel by pixel. And you often want 2 or 3 people labeling the same image for redundancy and calibration purposes. So it costs quite a bit of investment to be able to acquire a data set to be able to feed this AI algorithm. Of course, for an industry like urban transportation, it's worth it because it's literally a $1 trillion industry. But in many domains, this is really not something this is something that's cost prohibitive. So the bottleneck after supervised learning became so popular around 2011, 2012 is the availability of labeled data. And so what people did was, people started thinking about unlabeled data, and that led to these family of pre-training algorithms. So you take a large unlabeled data set, a data set you can collect easily via scraping or simulations or computation or whatever process. In this case, it's images. You just crawl from the internet. There are no labels, so it's very cheap to acquire. And you use a family of methods called self-supervised learning to learn an AI model that's also referred to often as an embedding. What this model learns to do is it learns to decode interesting features or properties of this image, like color gradients, shapes, and other things that it can detect from looking at, in some cases, billions of these images, but without any labels. What's interesting is that after you do this process, you take this embedding, use it as a representation of images, and then you train a very, very small model, sometimes just a linear model, on top of this embedding. And then with just a small amount of labeled data afterwards, you can actually build a decoder to make predictions, matching the accuracy of the fully supervised approach and sometimes exceeding it, sometimes with less than 1% or 0.1% the amount of labeled data. So this family of algorithms and its usefulness was a massive breakthrough. It started evolving around 2014 or so. And what we know of today as foundation models is just this type of idea, plus a few extra ideas, scaled to massive internet scale data. So you take all the text on the internet, you put it into a model using these types of self-supervised pre-training approaches and some other approaches like alignment, which I won't get into, and you get what's called a foundation model. And what's interesting about these types of foundation models is that if they're actually trained on text, like GPT, ChatGPT, then if you want to build a custom decoder to decode tasks for you, sometimes all you need to do is give it a language instruction. And now you have a decoder. And so what you see here over the last 15 years is a trend towards literally exponentially more cost-efficient decoding in both cost and time. And this is what has made AI such a hot commodity in recent years. You can now build AI systems for many tasks because of this trend, from autonomy to knowledge work. How many of you used Cursor, GitHub Copilot, Codex, Claude Code? Okay, I encourage more of you to use it. I use it all the time. And of course, very many areas of science as well. So now you might ask the question, well, what are foundation models? What is this new terminology? And since it's a scientific audience, I will throw the question back at you and ask, what does it mean to be alive? Is a virus alive? No. What does it mean to be conscious? What animals are conscious? What state of brain activity means consciousness? And the reason why I ask these questions is because there is no sharp boundaries to these definitions. Roughly speaking, the vernacular of what it means to be a foundation model is that it's a model that's been pre-trained on a large amount of background data set using self-supervised learning primarily, although not exclusively, such that it can be very, very, very efficiently adapted to some task-specific decoding task. Exactly what it means by large, background data set, task-specific, efficient, these definitional boundaries evolve over time, but that's sort of the intuition of what is a foundation model. The most important thing is that you don't start from scratch. So for example, you can go beyond language foundation models. Vision foundation models are very popular. You train a large background corpus, you get an embedding, and you can very, very quickly build decoders very efficiently for many new tasks. My favorite vision foundation model currently, although it might change in the next year, is called Dino. It's from Meta AI. And what you're seeing here, it's trained on just a ton of images. And what you see here is what you see here on the left is a three-dimensional color encoding of the PCA components of these images that Dino was trained on. And it's able to recognize this from looking at lots of images that the wings of the front of the wings of the bird is in a similar part of this embedding space as the front of the wings of an airplane. What does that mean? That means if you want to train a decoder on top of this representation, you can do it very efficiently. My favorite example is in the bottom right. So what you see there is a correspondence between a cartoon of a dinosaur and a fossil of a dinosaur. And a human made a few annotations like correspondence of the snout, correspondence of the tail, correspondence of the neck, and then you could train a little decoder that can make these kind of correspondences. That's pretty cool. You can also build foundation models for autonomy. One of the most popular areas in this space, at least in autonomous driving, is called building world models. A world model is basically a generative foundation model that has some notion of dynamics. In this particular case, this is a model that's been trained on data collected from autonomous driving, from both LiDAR and camera. This is called NeurAD. This is not my work. This is a project that you can actually use. It's used commercially, and it can actually sort of re-simulate other various scenes very cost effectively. That's sort of the value of having these world models. And so once you train one of these world models, you can use it as a simulator that's very, very flexible and contextual. So here's an example from this company or group where you have the original image on in the second. You have this original image in this column, and then the next two columns on the right are relighting it under different conditions, like it's dark or it's raining, but otherwise it's the same scene. So now if you want to test the perception system with your self-driving car, you can first test it completely virtually in this environment, which is substantially more cost-effective than collecting data physically. So more generally, though, real systems have very complex requirements. This is probably one of the reasons why we're both excited and scared about using AI in space assets, right? This is an actual quote from Aerospace Director when he visited Caltech several years ago. I won't name the company, although it may have manufactured this Boeing 737. He told me, Yisong, I want to use deep learning to optimize the design, manufacturing, and operation of our aircrafts, but I need some guarantees. Okay, and obviously in space you want an extremely high degree of situational awareness. That's part of the reason why we're talking about these one-shot adaptivity missions, right? Part of that is just just a really, really high level of situational awareness. Space is not the only place where this is required. I also have various engagements with, for example, the US Department of Defense. Operations compliance, I recently learned that something like 30% or more of our GDP of the United States goes into like bureaucracy, paperwork, compliance. Whether it's in healthcare or school, how many of you have tried to reimburse for a trip at either JPL or Caltech and it took months? That's called compliance. So that, and there are reasons for that, right? There's safety reasons, safety with respect to like fraud and things like that. Those types of safety concerns, but they are complex requirements, just purely in the paperwork space. And valid inferences. So I do a lot of work now in AI for science. If you want, this is an AI generated image of a black hole that I worked on in collaboration with my colleague Katie Bauman. If you want to use AI to make inferences from scientific measurements, you better be damn sure it's not hallucinating. Because you don't want to be the one to retract a Nature paper and be like, oops, the AI hallucinated that image. It wasn't actually a black hole in there. So how do you know, for example, how to get valid p-values from this AI-generated black hole? That's a form of safety in the scientific inference domain. Okay, so, but having said all of that, if you really want to use AI and have really unlock the benefits of it, you really have to let it scale. The power of AI is realized through a combination of data, compute, flexible models, and scaling. And if you hobble that, you won't actually realize the benefits of AI. So you want a massive data set. You want to be able to train these large models, analyze data, have this really tight feedback loop so the model is able to be as accurate as possible in whatever metrics you care about. And often if you're building this for a mission, you want to then distill that into a small model that can run efficiently on deployed hardware. And so this is not just an academic exercise. This is quickly becoming reality, especially in the commercial space. So for example, one of the companies that I advise is called Terra. The CEO is a Caltech alum, Tony. And he built this foundation model that runs on commercial drones that can, in real time, achieve zero-shot generalization. So, or I guess you guys are calling it one-shot, but we call it zero-shot in AI. Zero-shot meaning we don't need any training data from the target environment. I guess you guys call it one-shot in that you get one chance. So it's just a little bit of a mix-up of vocabulary. But zero-shot means zero training data from the target environment. So for example, a very, very simple system just with a foundation model can, oops, does this play? Does this play? It does not play. Okay, that's okay.
You may need to click on that screen. Like move the mouse, it's an extended.
Oh, no, this one plays. Sorry. It is lagging. I apologize. Oh, here we go. Okay, sorry, it's a little bit lagging. Basically, the drone is just flying over this terrain. It's completely GPS denied. And its goal is to do basically SLAM without any bells and whistles, no SIFT features, no bells and whistles. You just feed in the raw camera video into the foundation model and it decodes SLAM. Super simple. Like if it works, the software stack is embarrassingly simple. And it runs on a drone. You see the accuracy on the right-hand side, where the ground truth is the gray line, and the predictions of this foundation model is in the colored lines with the colors being timed. And so this is actually, this type of drone where the Terra is in contracts with certain defense contractors to just deploy this. It dramatically simplifies the software stack. You could build multiple decoder heads on top of a model like this one. Okay, the second, just check out time. The second key is for building these systems reliably is, of course, you don't want the foundation model just to scale without guardrails. No one wants that. You do need guardrails, but you want guardrails that are compatible with scale. In many organizations that I talk to, from hospitals trying to do AI for compliance, to the US government, who I recently learned sometimes couldn't keep track of where their tanks are on the battlefield because some general needs to sign this paperwork to transfer the tank from this place to this place, and some colonel didn't sign it, and the paperwork got lost, and it takes hours to figure out where the tank is. Real story. This recording is distributed publicly?
Yes.
Okay, well, I won't name the general. To robots that interact in very, very dangerous environments, especially if it can come to contact. So one idea is to say, well, okay, we have our standard software stack, autonomous software stack. This is probably very familiar to anyone who worked on, for example, the Mars rovers, at least at a high level. What you really want is you want these certificates between layers in the stack so that you can certify that the input-output behavior is as advertised. And otherwise, let the internal components of these systems be black boxes. And then you can optimize all the components using AI as long as the certificates are satisfied. So the certificates define the guardrails, and otherwise you just let the AI scale. And so my assertion is that you can use AI to optimize any aspect, help optimize any aspect of this process. There's the overall system level design. There is the abstractions and certificates to satisfy contracts between layers. And then there's individual components, right? And in the bottom row if you specify an abstraction or a certificate, you can actually compile that into what's called a reward function. And then you could train your component level design using things like reinforcement learning to satisfy these certificates. Alternatively, if you already have a component, but you're not quite sure what it's doing, you can actually probe it using active learning approaches to define certificates. On the right-hand side, you can use system-level programming. You could actually just build like a coding agent to given these certificates and abstractions, code me a system. So if you allow a level of adaptivity on your space missions, you can actually ask a coding algorithm to actually build up a new architecture, at least software stack, on the fly. And of course, you can also do library design, which is where you distill lessons and you put it into your system design. And then of course, the left-hand side is something that we've been doing for a long time in AI, and that's if the system level and component levels are end-to-end differentiable, you could do end-to-end learning to optimize all the hyperparameters of your system. So one early example of this, and I just want a huge shout out to Hiro, who got me into this whole area with this project, which is MLNav, which is Learning Augmented Rover Navigation. It's an extension of eNav. And I won't go into all the introduce it into all the details, but it's basically for speeding up the computation of path planning navigation for the Mars rovers. And so this is a diagram that I think Hiro created. It wasn't me. A long time ago. But the thing is, this is sort of a system, and then you can ask the question, how do I use AI to improve the flexibility or the speed of this system without compromising guardrails? And in this early example, we did this manually, right? We identified that the collision checker, the thing in the red box, was the most expensive module. And if we can use an AI system to sort of replace 90% of its work, then the whole system gets much, much faster, especially for complicated terrains with a lot of obstacles. And Hiro is breathing very, very heavily because I'm probably misrepresenting some parts of it. But this is my take on it from an AI point of view. And I'll stand by what I'm saying. And so here's just one of the videos they made. This is a simulation based on reconstructed terrain. And the main thing I want you to point out here is that once there's a lot of terrain, like rocks, then you have to do a lot of searching to be able to find a path. And so in the next part of the video, you see, let's just move a little bit. Here is the machine learning accelerated one where it's able to prune a lot of the search space very, very, very rapidly. So it spends much less time thinking when it encounters this type of complexity, and it quickly finds a good path. Another example is a project that I collaborated on with Sunjo Chung, who's in the back. This is called NeuroFly. And the basic idea here is that you want to build a flight controller that is adapted to changing environments, in this case, changing wind environments, while maintaining high precision. And the key thing I want you to notice here is that you have this neural network that's a pre-trained representation that's been pre-trained on many, many, many different wind conditions. And after it's been pre-trained on many, many different wind conditions, you can use existing techniques from adaptive control to then adapt on top of this representation to adapt to wind conditions. So here's just an example. You see this drone. It's a commercial commodity drone flying through this tight obstacle ring while the wind drifts between 1 meter per second to 5 meters per second. And it's able to maintain its trajectory in the face of these wind conditions. These drones that I should just mention are mechanically very standard. They just have this augmented intelligence by having this pre-trained representation of different wind conditions. Okay, so the next thing I want to talk about are AI agents. AI agents are basically these AI systems that are essentially state machines, but the logic of the state machine is actually governed to a large extent by a large language model and not by traditional logic. And so why might this be interesting is if you want to be able to have an AI agent look at data from your mission and automatically produce hypotheses that are interesting, you want the agent to be able to run on board and be able to sort of write code, execute the code, evaluate the code, and iterate. This is just an example where we take data from a scientific experiment, and after a bunch of iteration, it produces a hypothesis, which is explaining some phenomena we detected in LIGO in this case. And so this is a general area called symbolic regression. So this is a video I stole from my colleague Miles Kramer, who's a professor at Cambridge. And so it's basically, the AI system is basically looking through a whole bunch of different hypotheses. These are all equations which you can express programmatically to find one that is parsimonious and yet fits the data really well. And we've been applying these ideas at Caltech to various scientific domains. Here's an ongoing project off and on with some astronomers where there is this law called the Keck-Schmidt law, which relates the density of gas in a part of the galaxy with star formation rate. And we asked the agent if it can improve the law, and this is, again, a very, very preliminary result, so I'm not saying that it's correct or good, but it's something that the agent came up with, where it added redshift as an extra variable into this equation because, of course, redshift is an indicator of the age of that part of the universe, so if it's younger, there might be more star formation. So this is interesting. I'm a little bit short on time, so let me just make my last point and then I'll wrap up, which is multimodal reasoning. So this is actually something I did yesterday. I told GPT, generate an image of a yellow ball, a blue ball, and a red ball. The yellow ball in the front and to the left of the blue ball from the perspective of the camera viewpoint. The red ball should be in between the two. The yellow ball should be twice the size of the blue ball by volume, and the red ball should be half the size of the blue ball by volume. So GPT did an okay job. It got some of the in front of the yellow ball, in front of the blue ball wrong. Not a huge deal. It got the volume completely wrong. And this is, of course, important if you want to be able to have adaptivity and situation awareness in many areas of science and autonomy, because that type of reasoning is required. And so just to give you one project idea, where we sort of are exploring this, well, we built a model called Find3D, where you take a 3D representation of any object and they can actually segment out different parts of the object. Like, like the vase, the base, or the flower, or the canvas, the easel, or the stand, or the canvas. When we started this project, there was 0 training data for this project. So what the student Zichi did was she built a data engine. This is in collaboration with Georgia Gilsari, who's a faculty member here at Caltech. And I'll just quickly walk you through what this system does. It takes a 3D asset, which we have a lot of. It renders it in 2D, and then it uses a 2D foundation model, an existing 2D foundation model called SAM, which is the segment anything model, to segment parts from the object. Then it asks another 2D foundation model called Google Gemini to label that part. So we actually used a 3D asset, standard rendering pipeline, and 2 existing 2D foundation models to generate these partial data points, which we then back project in 3D space, like this. And so we generated millions of training examples in 3D using this pipeline. And what this is it's a data flywheel. You have your existing data, you build a model, you use the model in interesting inference methods, that you use that to create new data, to create new models, to create new inference. The way to adaptivity, in my opinion, is to actually learn how to build these data flywheels, to exploit existing foundation models, to build simulations and data sets for next generation foundation models. And the last thing I'll mention, is that we're also working on AI for sensing. This is the big part of my area in AI for science, where we build AI sensing algorithms that are much simpler once they work than the kind of sensing algorithms you would build not using AI. And the basic idea is you have training data, in this case simulations of black holes, because we can do that using Einstein's theory of relativity. And then we put that into a foundation model. You collect observations, such as from the Event Horizon Telescope. You feed that into an inference algorithm, and you produce images of black holes that are consistent with the observations. So this is, of course, in collaboration with my colleague Katie Bauman. We've actually done this for a range of applications, from inverse light field scattering, compressed sensing, MRI, black hole imaging, which is radio wave telescopes, waveform inversion, which is seismometers, and Navier-Stokes equations using coarse images. So just to summarize, I think that I work on all these areas. I think the frontier is really about how do we get the data in a format that we can build a model for, let that scale as much as possible, and then figure out how to build guardrails that are compatible with that scale. So I'm happy to take questions. Thank you very much.